Hello, and welcome to this tutorial. I will walk you through how to set up a thermal simulation using ANSYS Fluent. We start off with the mesh geometry, and I will walk you through what the physics of the problem is. So here, what you see is basically a reactor where we have an inlet indicated by the blue vectors. And then we have an outlet, which is on this side with the red arrows over there. The bottom surface in this case is basically where we apply the heating. I have named this as a boundary condition where we can actually select that. And the entire chamber is filled with, basically in this case, the PCR mix. And we're modeling that as a simple fluid, and we're using the water properties in this case. So as you can see, the ANSYS Fluent has a menu on the left, and what we do is we can walk through setting up the physics by going through this one by one. It also has a ribbon on the top where the user is guided through setting up the problem. Let's just use the outline view to set up the problem. The first thing what we want to do is to go under General and essentially define the type of simulation we have. And in this case, it's a transient simulation, which means that we need to provide the temperature profile for the simulation. So how do we do that? One way of doing this is by actually reading a file. The file has to have a certain format, so I will show that to you in a second. But you would click on Profile, and the format would need to be either a CSV or a prof or tabbed. I've already prepared this file for you, so you can take a look at this. This is called the PCR profile. We would click on this and say OK. And once we do this, it would actually read, so we can see on the console that it read the file, and it contains time and temperature. So I want to show you also how this thing looks like. So here I have the temperature profile. I created this thing in Excel. It has basically the following format. You have two columns. The first one is always time, and then you have the second one is temperature. And as you can see, this is basically in Kelvin. So I've converted everything from Celsius to Kelvin. And the format needs to have basically a name, a unique name, and then the number here indicates the number of columns that you have. So we have two columns here. Then the next argument is basically the number of data points that you have. So this file basically contains 103 lines. The 0 here indicates if this is basically periodic boundary condition or not. So in this case, it's not. So that's essentially the structure. And then one thing to note is that when you save the file as text, you need to override this to change the extension from txt to ttab. Otherwise, Fluent would not be able to read this. So we successfully were able to upload the time and temperature profile and ready to move to the next part, which is essentially defining the model. And the model is simple. So we have essentially, it's a thermal model. And so if we double click on this, which is energy, you can see that it's checked off. One thing that you can see is that Fluent actually has a lot of visual cues to let you know what you have selected. So when it's blue, you can see that also on top that is turned blue. And all the other physics are actually white, which means that they have not been selected. And so in this case, since this is just a simple flow, and we're also looking at if there's any mixing involved due to heating. So I've turned on the laminar and the viscous. And this is basically all the options that we have. Obviously, because this is a small device, we're looking at laminar flow and nothing in the turbulence. And the next thing we do is define our properties. So materials, in this case, as I mentioned, we have everything is defined as water. So the entire chamber is filled with water. So it's a single phase problem. And I copied this from the Fluent database. So you can just click on this and then copy and move it over. There's no solids, but this is how basically Fluent always comes as default with a solid in here. We can ignore that at the moment because this is basically a fluid simulation. Next, we need to define what's basically inside the geometry. In this case, this is our geometry. If I do a right click and edit, you'll see that it takes me to this panel. And I have selected water liquid as the material that I want the entire geometry to be filled with. All right, now next thing is to apply the boundary conditions. So we do have an inlet and outlet, but since nothing is flowing, we have left this as default. The next thing we need to do is define the temperature profile at the bottom. So I've named the boundary conditions, the bottom of the chamber as bottom. So we can double click on this and you'll see that it has what's called the temperature profile. So in the selections, you can have constant, you can have what's called the UDF or profile, and that's where I've selected the temperature profile. We'll leave everything else as default. Oh, as a matter of fact, there's one more thing that we need to do is that we are assuming that there's some heat loss due to natural convection on the other surfaces. So you do this by basically selecting all the other walls and selecting a heat transfer coefficient. In this case, I selected 10 and room temperature, which is at 26.85. Okay, we're ready now to actually move into how to set up the solution. And we can bypass these because these are related to dynamic mesh or reference frames, which we're not using. Named expressions, we don't have that. But if we did, we would basically add them here. So under solutions, the first thing we got to do is go under methods. We would take basically the default. In this case, there's a number of different solvers that exist. Simple is a good one. We want to make sure that these are second order upwind. And we look at the control panel in this case. And again, we take the default. And we also can look at basically the residuals and in terms of what we want to set as the criteria for a convergence. So I picked a pretty stringent values to make sure that this is basically solving and is completely converged. And now we're ready to actually do a final step, which is basically setting up the run calculations. And in this case, the run calculations, one nice thing about it is this check case, which I highly recommend. It gives you some information. It usually has this message saying that, check your mesh, so we can ignore that. But then if there's any issues with the model, it would actually give you some hints. So that's really nice. So now, since this is a transient simulation, we have to define basically 3 different variables. One is the number of iterations. So this is the number of iterations per each one of the time steps. Second is the total number of steps. So this, for example, in this case, I have 0.2. So it would be 0.2 times 500 would give me the actual time. So At every iteration, it's moving at 0.25, and it's basically iterating 40 times, and it would either go to 40 iterations or the convergence criteria, whichever comes first. So you're ready to basically start this. The next thing you got to do is initialize. That's basically the initial condition. I recommend using hybrid initialization. So we would click on initialize, and that would essentially start the simulation. And for the sake of time, I will basically show you the final results. And in this case, we would go under results, surfaces, and you can define basically planes. In this case, I have defined a line and a plane, and you can also create a mesh or contours. So let's take a look at one of the contours. In this case, if I double click on this, I can see that it's basically selecting the bottom in basically inlets, outlets, the plane, and the solid. So we can compute and display this. And you can see that we can look at the maximum and min. So here, the minimum temperature was 25 degrees, which was the room temperature. Maximum was 93.85. That came from our temperature profile. And we can see that this is a time step. So this is basically it's a times that's 4.2 times e to the 1 seconds in the simulation. We can also look at a contour, in this case on a plane. So I can show you that. And notice that basically we can see that in this particular design, because of the fact that we're heating only from the bottom, we never reach the set temperature, even during the time that it's actually staying at that temperature. So this tells us that this design basically will not work, and we would need to implement another way of heating. And one simple way would be to actually add a heated top. And so this would become actually tricky because from a PCR point of view, you need to also have optical clarity to be able to take measurements of the signal. So by simply having a heated top, it will basically solve the thermal problem, but it won't solve the optics. So we need to come up with a clever way of addressing this and be able to achieve the temperature uniformities that we're looking for. This concludes this tutorial.